Hello friends, here in this video we are going to see a problem based on Otto cycle. Here is a question. Whatever is given in this question, I'll write that in the form of data first. Let us get started. Now it is given that in a constant volume Otto cycle, the type of cycle is given, so I'll mention the type first. Otto cycle. Next, the pressure at the end of compression is 15 times that at the start. So the meaning is pressure at the end of compression is P2 and it is 15 times the pressure at the start, which is P1. So this is the other way of saying that the pressure ratio is 15 because P2 by P1 will be 15. Next, the temperature of air at the beginning of compression is 38 degrees Celsius. So at the beginning of compression means T1, that is 38 degrees Celsius. So it will be 38 plus 273. So therefore T1 will be 311 Kelvin. Next, and maximum temperature attained in the cycle is 1950 degrees Celsius. So maximum temperature will be T3. This I'll explain once I draw the PV and TS diagram, that how it is T3, the maximum temperature. So 1950 degrees Celsius, it will be 1950 plus 273. So T3 value will be 2223 Kelvin. Next, determine compression ratio, the first question. So compression ratio is R suffix C. Next, thermal efficiency of the cycle. Since the type of cycle which we are using here, it is Otto cycle, so here we have efficiency of Otto cycle. And work done. So work done is, I'll write down WD. Next, take gamma for air as 1.4. Gamma is 1.4. Now, with the data available, let us try to get the solution to this problem. Now, in the solution part, the first thing I'll mention is PV and TS diagram for Otto cycle. Now while drawing the PV and TS diagram, it is a graph. PV diagram is the pressure volume diagram and TS diagram is temperature entropy. So this is TS diagram. Now, in case of Otto cycle, there are four processes. The first one is reversible adiabatic, or it is also called as isentropic process. And that process is shown with the help of a curve. So during process 1 to 2, at point number 1 the volume is V1, at point 2 the volume is V2. Now if we see, during this compression process the volume goes on decreasing from V1 to V2, but there is rise in pressure from P1 to P2. So this is the reversible adiabatic, or we can say isentropic compression. After that, the second process is constant volume heat addition. Otto cycle is also given as, it is also called as constant volume cycle because the heat addition takes place at constant volume. So point 2 to 3 indicates constant volume heat addition, and V2 is equal to V3. Then after this, reaching point number 3, from point 3 to point 4, the next process would be called as reversible adiabatic or isentropic expansion. So again, that expansion process will be following a curve like in compression process. So process 3 to 4 is reversible adiabatic or isentropic compression, wherein, as we can see, the pressure drops from point 3 to point 4, but there is increase in volume from V3 up to V4. V1 is equal to V4. So this is the reversible adiabatic or isentropic expansion. Then process 4 to 1, it is constant volume heat rejection. V1 is equal to V4. So here I'll mark that process 1 to 2 and process 3 to 4 both are reversible adiabatic process. It is given by the law PV raised to gamma is equal to constant. Then during process 2 to 3, the heat is added. So it is QA. 4 to 1, heat has been rejected, so it is QR. Now here I have denoted the processes on PV diagram. Similarly, I can denote them on TS diagram as well. So on TS diagram, process 1 to 2 is reversible adiabatic or isentropic compression. It is shown by a vertical line on TS diagram. So during process 1 to 2, the entropy remains constant, that is S1 is equal to S2, and there is rise in temperature from point 1 to point 2. Process 2 to 3 is constant volume heat addition. So during the constant volume heat addition process, temperature will go on increasing from point 2 to point 3. And there is also an increase in entropy. So here during the heat addition process, temperature has increased and heat has been added, which is QA, Q suffix A. Next, after reaching point 3, 3 to 4 will be isentropic expansion. Isentropic expansion, and as we see, during the expansion process, temperature drops from T3 to T4, and that drop in temperature is utilized as the work output. Now process 4 to 1 is constant volume heat rejection. So again there is a constant volume line, and here the heat gets rejected from point 4 to point 1, and it is at constant volume. So this is heat rejected at constant volume. Next, during process 1 to 2, there is compression taking place and work has been input to the system, so it is W suffix C. During process 3 to 4, there is work output, which is W suffix E, which is the work we are getting in expansion. Similarly, here I can show in 3 to 4 we are getting work output, and in 1 to 2 process we are giving the work input to the system. Now with the PV and diagram, TS diagram in front of us, here as we see in the question, it was given that regarding T3 they had said that it was the maximum temperature attained in the cycle is 1950. Now this maximum temperature attained in the cycle, it is nothing but point T3. So T3 will give the maximum temperature, and in the data previously I had written it as T3 itself, because at T3 the temperature would be maximum. So now here, as I have explained, T3 is the maximum temperature. It can be seen from the TS diagram. And now the first question is, we have to find out what is RC. RC is called as compression ratio. So to start the solution, the first part would be calculation of compression ratio. Now I'll write down, since for process 1 to 2, the relation, it can be written as T2 by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma, or it can also be said as V1 by V2 raised to gamma minus 1. Now this is possible for process 1 to 2 because it is reversible adiabatic or isentropic compression process. Now one more relation can be written, and that can be in the form of PV raised to gamma is equal to constant. So I'll write down that during process 1 to 2, it can be written as also P1 V1 raised to gamma is equal to P2 V2 raised to gamma. I'll write down, since it is reversible adiabatic or isentropic process. Next, after reaching at this stage, if I look into the problem, we have the relation of P2 by P1, that is P2 by P1 is equal to 15. So I'll keep P2 by P1 on one side and bring V1. Here we have V1 raised to gamma, V2 raised to gamma will be in the denominator. It is equal to P2 by P1. Therefore V1 by V2, I'll take them, and common raised to gamma is equal to P2 by P1, which is given as 15 in the problem. V1 by V2 is nothing but it is called as compression ratio R suffix C raised to gamma is equal to 15. Here I'll write down where R suffix C is called as compression ratio and it is equal to cylinder volume upon clearance volume. So it is V1 by V2. Next, therefore, here I'll send gamma onto the other side. So therefore RC will be on one side and here I will have 15 raised to, now this gamma when it goes onto the other side it becomes 1 upon gamma, and here I have 15. Gamma is given for air in the question as 1.4, so it is 1 upon 1.4. Therefore the value of RC on calculation will be 6.91, and this will be the first answer for us. The first answer. Next, the second question, after RC we have to calculate efficiency of Otto cycle. So here I'll write down calculation of efficiency of Otto cycle. Now to calculate the efficiency of Otto cycle, I'll write down, since efficiency of Otto cycle is given by, the formula is 1 minus 1 upon RC raised to gamma minus 1 therefore efficiency of Otto cycle is 1 minus 1 upon, now RC is 6.91 raised to gamma is 1.4 minus 1, so on calculation I'll get the efficiency as 0.5384 or 53.84% if I multiply it by 100. This will be the second answer. Now the third question in this is we have to find out the work done, so I'll write down calculation of work done. Now since I can say that work done, which is WD, is equal to heat added minus heat rejected, because if we see in the PV and TS diagram, then we can say that out of the heat added, from that if we minus the amount of heat which is rejected, we are going to get the work output from the system, which is WE. So therefore work done will be heat added, that is QA, minus heat rejected, which is Q suffix R. So I will keep them as equation number 1. Now we need to individually calculate the value of QA and QR, and first I'll write down, I'll start with QA. QA is the heat added, and as we see in case of Otto cycle, the heat is added at constant volume, so I'll write down therefore heat addition at constant volume is given by QA or Q suffix A is equal to mCV into T3 minus T2. Keeping this as the second equation, because as we see here, the heat is added at constant volume and the temperature difference is T3 minus T2, so it is mCV T3 minus T2. Now out of this we can say that we have the value of T3 which was given in the problem. I'll show it in the form of data. Now here T3 value was the maximum temperature, it is 2223 Kelvin, so T3 value we have. Next CV, now CV value we can assume for air, and mass we can take it as 1 kg, so the only unknown which remains is T2, so we have to find out T2, and for that I'll write down since for process 1 to 2. So now, since for process 1 to 2, the relation can be written as T2 by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma, and it can be also equal to V1 by V2 raised to gamma minus 1. Now from this relation I'll calculate the value of T2. So therefore the value of RC we had calculated, it was 6.91, and RC is nothing but V1 by V2. So T2 by T1 can be made equal to V1 by V2 is RC, that is compression ratio, is equal to gamma minus 1. I'll write down, since RC is equal to V1 by V2 and it is called as the compression ratio. Now therefore T2 is equal to, T1 value is given T1 is 311 Kelvin. So I'll send T1 onto the other side, 311. RC value we have found out, it was 6.91. Now gamma for air, it is 1.4 minus 1. So on calculation of the entire terms here, I'll get my answer of T2 and it comes out to be 673.83 Kelvin. Now once we have calculated T2, I'll write down, assuming mass of air as 1 kg, so therefore M is equal to 1 kg, and specific heat at constant volume CV, C suffix V, is 717 standard value kilojoule per kg Kelvin. So these two values I am assuming here of mass and C suffix V, that is specific heat at constant volume. Now after reaching this stage, I can put all values in equation number 2. So I will get the answer of heat added. Therefore put all values in equation number 2. So we have heat added Q suffix A is equal to, it was M into CV, mass we have assumed 1 kg, CV as 0.717. Next T3 minus T2, T3 value is it was 2223 Kelvin minus T2 value we have calculated just now, and it was 673.83. So therefore on calculation I'll get my answer of QA as it comes out to be 1110.75 kilojoule per kg. So this is the amount of heat added. Now similarly I'll calculate the amount of heat rejected. So therefore heat rejected at constant volume is given by Q suffix R is equal to mCV. Now the temperature difference will be T4 minus T1 because it is rejected from process 4 to 1. Now I will keep this as equation number 3rd. Equation 3. Now here if I see M, CV and T1 values are known, only unknown is T4. So for that I'll use the process 3 to 4. I'll write down, since for process 3 to 4 T3 by T4 is equal to V4 by V3 raised to gamma minus 1. Since it is reversible, adiabatic or isentropic compression, or here since it is expansion, so it will be isentropic expansion process. Now if I can see here, T3 by T4 I'll keep them as it is. V4 by V3 can be made equal to, V4 is equal to V1. V4 is equal to V1 because it is constant volume heat rejection. Next, V3 is equal to V2, constant volume heat addition, raised to gamma minus 1. So therefore this T3 by T4, now V1 by V2 is nothing but RC, that is compression ratio. So here we have to find the value of T4. I'll keep T4 on one side, and here this will be T3 upon RC raised to gamma minus 1. T3 given in the problem 2223 Kelvin upon RC. RC value was our first answer. It was 6.91, gamma 1.4 minus 1. So from this I'll get the answer of T4, and it comes out to be 1026 Kelvin. Now after getting T4, again we are going to assume mass as 1 kg, CV value as 0.717 kilojoule per kg Kelvin, like in heat added process. So I'll put all the values in equation number 3. So therefore put all values in equation number 3. Now in equation 3 we are having it as mCV T4 minus T1. So I'll put the values. Therefore Q suffix R will be equal to M is 1 kg, CV is 0.717 kilojoule per kg Kelvin. Next, T4 value we have found out, it is 1026 Kelvin. So 1026 minus the value of T1. T1 is 311 Kelvin given in the problem. So if I calculate this, my answer of heat rejected at constant volume comes out to be 512.66 kilojoule per kg. So this is the amount of heat which has been rejected. So now here we have the value of heat rejected, which is 512.66 kilojoule per kg. So once heat rejected and heat added have been calculated, we can put their values in equation number 1 to get the answer of work done. So here I'll write down after this. Therefore, put Q suffix A, that is heat added, and Q suffix R, that is heat rejected, in equation number 1. So therefore we have work done is equal to, now QA value, it was 1110.75 minus heat rejected is 512.66. So therefore from this I'll get the value of work done, and it comes out to be 598.015 kilojoule per kg, and this will be the third answer. So here, if we see in this question, there were 3 things asked. First was RC. RC is nothing but compression ratio, and that compression ratio was found to be 6.91. So this was the first answer. So we have calculated the compression ratio. Next was the efficiency of Otto cycle. That efficiency came out to be 53.84%, the second answer. And the last question was work done, and that work done value was found to be 598.015 kilojoule per kg. And with all 3 unknowns, we have found out their values, and with this we can say that the problem has been completed.